do it off that today. Okay, thanks guys. So a couple quick announcements. First, I gave you guys Monday to play around with the VTNA stuff like that. I hope you guys took an opportunity to sort of work through that part. That's the practical sort of application VTNA based on the sort of experimental results we gave you on Friday. Again, that's an exercise I want you guys to complete and be sort of familiar with. Your midterm will definitely involve applying VTNA on some data set. So if you're having trouble struggling through sort of using that sort of worksheet or extracting point to it, please make sure that you flag it, because I will ask you guys to sort of work through this part for one of your midterm applications. Also, now I gave the problem part of it, so this is an exercise part I want you guys to work through. It's posted up online. This is another sort of example of an application of the TNA component, but also now combining it with Copacity. The thing I want you to do there is to also basically work through the VTNA template, try to apply how that application could work for interrogating a mechanism. The mechanism I'm proposing to you guys, we worked through this on Friday, will not fit the data you have. It's insufficient because it's missing a deactivation component like we talked through. So the goal here is, given the data you have and the ability to create a new model, what's missing? Like as we talked through on Friday, the mass balance didn't seem to make sense, so there's clearly something missing in that catalytic system that you have to add in. So it's going to basically work through that exercise. Try that point, same thing like last time. Please hand in the thing on Sunday. We'll talk through the sequence on Monday as far as a working problem set. Last one too, check your schedule for the presentations. I shuttled a couple people because there was some travel going on, so I've now moved them, I think, to accommodate anybody who's emailed me. Please check the new updated schedule, that I haven't created a new problem by moving somebody where you thought you were free. I think it shouldn't have been big. Basically, what I tried not to do is, if you were very late in the sequence, I didn't try to bump you to first week or something. It's meant to be a small perturbation, but take a look if there's any sort of shift and slide. Okay, we're going to jump into a little bit more classic theory part that's an application of sort of the topics we've been building up. So this is much more classical physical organic chemistry and application of that part. We're going to talk through specific acid-base catalysis. Now, has anybody heard of that term before, specific and general acid-base? If anybody's ever done another physical organic, this is it's a bad joke that, I don't know why physical organic chemistry did this, but these two are examples of a continuum of sort of reaction analysis. We're trying to emphasize that catalysis or any reaction sort of exists on a gradient. SN1, SN2 is what we've usually sort of introduced you guys to reaction dynamics, but if you look at it, SN1 and SN2 are kind of the same reaction on a continuum of which bonds break in which order. So we're just going to emphasize that in the process of catalysis. That's what these two are for. We'll start talking about Bronsted acid catalysis roles and then energy surfaces. So we've kind of been going through, talking through majorly kinetics, which is talking about activation barriers. Slow steps and stuff, remember we talked about this, where if you look at an energy surface like this, we have this concept of which is the rate limiting or turnover limiting step. That's the concept of highest jump versus biggest barrier. And you guys should be sort of comfortable looking at these kinds of diagrams of, okay, I have two transition states, I have one intermediate, I'm trying to express that I go from one starting material to one product on this kind of surface. But really, this kind of perfect view of how a system looks in terms of two separate breaks, what you can get is a gradient of reactivity from this we would normally classify as what is a stepwise mechanism. There's a single step. The reaction takes a breath and does a second step. But even for the same class of reaction, let's say an acid catalyzed process or a rearrangement, you can actually have, depending on different substrates and different catalysts, a continuum that starts to walk from the clearly stepwise one, where there's a well-defined intermediate, up to something where there becomes almost this very basic shoulder to the point where it almost completely disappears. So you actually can get different continuums where the intermediate, if it's relatively unstable, or if this first barrier becomes relatively stabilized, you can actually collapse together those two steps into something that was considered to be concerted, or even sort of like stepwise but discontinuous. Dean Tantillo was the one that really taught me this point. Does everybody know Ken Houck? Is that name familiar? Ken Houck is kind of the main god of physical, organic, mechanistic, computational chemistry. He was trained by Woodward and sort of the classic synthetic people, and then he was the one that really brought DFT to the sort of the organic chemistry community. Dean Tantillo is one of his main compatriots, and he's a very, very, very articulate organic chemist, but computational. The way he likes to think about these processes, you can think about it in terms of you play a game of patty cake on the desk. Stepwise is 2 discrete steps. So you have a 1, 2 kind of point. Concerted means 2 steps, same time, right? Both hit at the same time. But what you can also get is, right, where you get this near close between the two, where that gradation or the distribution between the two is tight or irrelevant. So first thing is just to get this idea around that we do not live in these nice simple buckets. All reactions, even for the same class, exist on a continuum, and we usually, just like SN1, SN2, we define 2 perfect archetypes at 2 very far extreme cases, and we use those examples. But remember, as you change either catalyst, condition, substrate, solvent, you can actually blend between that entire system. There are cases that look kind of SN1, SN2 at the same time, right? It's not exactly perfectly SN1 or SN2. You can get something that's that would be kind of more SN1, where there's this discrete step in between to make a carbocation, but it's not a full SN2 with inversion, so there's actually nuance. An example of this is what we call these 2 pairs of acid-base catalysis. Now we're talking about Bronsted theory here, but the same applies for Lewis acid. When we say specific, and this is why it always confused me, when we say specific acid catalysis, what we're really saying is the specific acid doesn't matter. Now that always confused me, because if you're talking about specific, then it should be specific matters. But in fact, it's the reciprocal. If you're talking about specific acid catalyst, the thing I want you to remember is specific acid catalyst means the specific acid doesn't matter. It's only the concentration of H3O+. Now what we mean by that is, imagine you have an addition to a carbonyl. In this case, it's ester hydrolysis. If I'm going to do this addition, it's going to be a multi-step acid catalyzed process, where the first thing I have to do under acidic conditions, I will activate my carbonyl and make it into a better electrophile. I'm going to do a nucleophilic addition. This second step here, after activation, is the slow step. And then after that, you're dumping the proton from your neutral nucleophile. If water was the thing that attacked, water has to pick up a proton. So this is the classic hydrolytic sort of mechanism that you guys have seen. It's the backwards version of the Fischer esterification, right? Under acidic conditions, with water, you're just doing Fischer esterification, saponification under acidic conditions. Everybody's seen this kind of thing before. Why we say specific acid catalyst here is, I don't care what acid you add, it's just protons. So I could use sulfuric acid, phosphoric acid, HCl. You're basically saying that in these cases, the relative pKa of that first acid is not the driving force, it's how many protons you have. And the rate will be identical if I use the same concentration of HCl, phosphoric acid, sulfuric acid, as long as I match the proton component. In other words, as long as I match the H3O+ concentration or the pH, the rate will be the same. It doesn't care about the identity. So this is a typical example of, almost like SN1-like. You have to activate to make an intermediate. That's fast, but then the second jump is your turnover limiting step. Wow. That's going to be annoying. Should we open the door and just dude? So let's sketch out the energy level diagram. Here we have how many steps? If you look at kind of what we're articulating in a major way, how could we potentially break this down? How many transition states do you think we're drawing out here? 6, right? We've got activation, some slow step for nucleophilic addition, proton transfer, nucleophilic collapse, proton loss, right? Now, one of the simplifications we can make, every step after the slow step, we're going to bin together, right? The turnover limiting step is number 2. That means we're going to simplify the back half of that into that's just downhill, right? So let's do that part. So if I was going to try and sketch this out, first thing I'm going to do is I will define my starting state. Your starting state is encompassing everything that's in this system, which is your starting material, your acid catalyst, your solvent, right? That's everything in that first box over here. If we've drawn this out, we said that there's a fast step to a high energy intermediate, and then a slow step to make your tetrahedral intermediate, and then we're going to say fast after that. Where should I put this guy? So we're saying this to this is my first step. There's a transition state associated. Where does that state go on this energy level diagram? Above or below my starting material? So I got a thumbs up above. Everybody agree with that? So up here somewhere, right? Because what we're saying is I'm increasing the energy of the system to make an activated intermediate there. If you say fast, now again, this is fast or faster. We're not saying it is quick on the global scale of the universe. We're saying for this system, it's going to be fast. This is where I can already see I'm going to need more room. Let me redraw this. Can I do this? Oh, yeah. I don't have to do squats the entire class. This is good. Okay, starting material, intermediate 1. Okay? Now, next step. Am I going to be higher, lower, equal? This is a rough guess. Open debate, but like, what are you guys thinking? I see one lower, maybe.
I would say maybe a little higher, just because of tetrahedral intermediate, and there's like still the charge conserved.
Okay, so you're saying you lost a pi bond, which is maybe destabilizing, and you're at least still charged, so you're kind of in the same range, maybe? That's fair. Why would you say lower? Again, nobody's wrong here. This is the process. You got to work through your hypothesis. Why might you say lower? But what made you, again, it can be anything. You can just say, I feel like it, if that's the point. But do you have any other basis of like why it might be lower? No, just felt like it? That's fine. Can anybody come up with a reason why it might be lower? You're not wrong. There could be cases. Yeah. Okay, good point. So what you're saying is where the proton sits is going from an sp2 protonated oxygen to an sp3 protonated oxygen. Which is more electronegative? Do you guys remember? sp2. So probably against that, right? I think, right? If the sp2 center is more electronegative, it's holding the center charge closer, it might be easier to protonate, so the sp3 oxygen might be less. Is that right? Yes. Good call. The positive charge on an sp3 center will be less painful than a positive charge held close on an sp2 center. Back to classic Chem. There is a parameter you can use to rank these, pKa. Does everybody remember the pKa of protonating a carbonyl versus protonating water and oxygen? These are both negative, right? Positively charged oxygens are going to be less than 0. I think it works out that, yeah, a protonated oxygen about is like -2, -5. Protonated carbonyl is probably -7, -9. So yeah, that's consistent, right? It is a much stronger acid when you start out here. So going to a less acidic center might give you a bump. Now again, that's a single center versus overall composite. At either way, we're going to say it's in the neighborhood, right? I don't know exactly how much up or down it's going to be, but for now, let's say we might be gaining some things of stabilization of where the charge is, but yes, we're paying a price of blowing away a pi bond. Don't know, right? But it's not down here, right? We're not at the end of the line. We're not similar to starting material. We're still somewhere in the upper manifold. Okay, and then we're saying after that, everything else that happens, we get to a product which is, if you look at the constituents, we're making a carboxylic acid and we're kicking out an alcohol. Now we are at least comparable to our starting material, right? We're going to be the same relative area. We're not going to something that's so massively stabilized relative to your ester, right? We can sort of say thermodynamically, this system, and if you remember back to first, second year, for these kinds of hydrolytic reactions, we drive them by mass transfer by Le Chatelier, right? If you remember back to Fischer esterification, They work because we dump in a buttload of alcohol and we dry the system. So these are primarily driven thermodynamically by amount of material, not by energetics, right? We're kind of on the same surface. Okay, so we constructed a diagram. Now if I had to add the barriers, what might this look like? First step is going to be fast, so I'm going to put just a hop there with a relatively small retro. It means that it's quick, can happen quickly, but the retro reaction is going to be very easy, right? Losing that proton is going to be a fast equilibrium. The next step, what do? We have to go higher than this transition state, and I'm going to try and, right? If I really wanted to exacerbate this, I'm going to do delta G double dagger 1 and delta G double dagger 2. I want to set this up so delta G double dagger 1 is much less than delta G double dagger 2. That's probably my ideal state, which is going to give me the K values when you go through Arrhenius, that reflects this, right? The second K value is going to be much larger than the first forward one, but the retro reaction is going to be comparable. That makes sense? Everybody sort of clear there? And then probably after this, I'm just going to say dotted line. Doesn't matter really after that much more. It's just stuff's going to happen. Don't care, right? So what we're saying is, and this is why this diagram looks like SN1. If you guys remember what those diagrams look like, you have a fast equilibrium initially. That would be like losing water or your chloride to make your carbocation, a high energy intermediate. The problem, the second step, the nucleophilic addition in something like that might be, okay, sorry, I'm wrong. Damn it, I blew the transition. Fast reversible followed by rate determining, that's what we're dealing with here. SN1, what's different about SN1? Let's say I took a chloride to make a carbocation intermediate and then nucleophilic capture. That's your highest energy intermediate. This is probably easy after that. Making this is harder. So your first barrier is slow here, second is fast. This would be true for an SN1 where you had to protonate first, right? If you had to protonate alcohol, then let it to leave, then we're in the same kind of camp. That's true. But a standard SN1, you're probably going to have the first step is hard. That's why the electrophile is the only thing that shows up in the rate constant. Okay, so the purpose of this point was, number one, drill in you guys, specific acid, just as talking about the specific acid doesn't matter. It's only the relative pH of the system. Having more acid will tend to populate more of this intermediate, which will help the reaction go faster. This is under saturation kinetics, and we just need to have a higher concentration of that first intermediate. That's what will make the reaction go quicker. But it doesn't matter if I'm talking about other systems. Generally, this is what it looks like. Here's the rate equations that come across it. And again, what we're focusing on here is the rate of the overall system, if you do the steady state approximation, will show that your acid concentration, that's your catalyst, your substrate concentration, and as long as this concentration is constant, your K and your second constant will all just collapse together to be your observed rate constant. So this matches the kind of algebra that we talked about in the first couple classes. It's the same solution that we did when we talked about a fast pre-equilibrium approximation, where we have a fast equilibrium followed by a slow step. The other side, the complete other end of this, is what we call general base catalyst. This is where it really matters which proton you have. The structure of that, or the specific catalyst you use, is really, really important, because what you're actually doing here is we're collapsing those two steps into one step. Protonation and nucleophilic attack happens at the same time. The perfect example, if anybody remembers biochem, is glycolysis. This is where I have an enzyme. My enzyme is going to both be my nucleophile and my acid catalyst. So what has to happen here is I have to form a very structured transition state. My acid catalyst is involved in what is, it ends up looking kind of like a ternary reaction system, right? Where the proton we're adding, where that catalyst is coming in for activation, and the nucleophilic attack, it collapses together to become something that looks almost like an SN2 reaction. Both pieces are happening at the same time. Why this is possible in this case is because you take an acid like a carboxylic acid, something that's very, very, very weak, That proton on its own is not normally acidic enough to just protonate the glycosidic bond. You're going to have some reason where the enzyme, the pocket of the enzyme, presents that proton in such a way that the nucleophilic attack and protonation are coupled to each other. This is how we look at sort of the same thing kind of happens on proteolytic enzymes. If you guys remember the sort of catalytic triad of proteins for hydrolysis, this is where you have an acid, a nucleophile, and some type of an imidazole that's used for hydrolyzing an amide bond, right? If we're going to have an enzyme that's doing this, you have the same kind of presentation. So the difference with the general acid catalyst here is the catalyst is also the nucleophile. They're usually paired together. The proton transfer and the nucleophilic capture happen in the same time in the rate determining step. This is something where like chiral phosphoric acids would do the same sort of thing, where the shape and geometry of your acid really matters for this turnover. All that happens here is this. Now what you're doing is the overall diagram is the acid catalyst, your substrate, and water are in one step. You have a single slow step, and then everything after that is fast. So if you're going to redraw, what we get is something that looks more like you have your substrates, you have a single hard step, and everything else is downhill. What we're doing is collapsing these two discrete steps, activation and the nucleophilic capture, into one transition state which is organized. The overall barrier relative to these two may not be comparable to each other, but what it means is you don't have this case where there has to be this discrete formation of a protonated intermediate. You're getting this overall handoff. It's the closest thing to like an authentic ternary reaction system where you have proton, nucleophile, and substrate all in the same place at the same time. But it's still really made up of three discrete steps. You're still doing proton transfer and nucleophilic capture. It's just it has to happen in an organized transition state that requires you to have a specific one. Again, I keep using specific. That's why I keep getting confused on this point. But yeah.
Are there, like, it seems totally feasible for an enzyme to do this. How hard is it to come across this in
The real world?
Yeah.
Where you get it, or the closest version of this, very hard is the quick answer, right? Because by definition with this kind of acid-based system, you must have proton transfer and nucleophilic capture all in the same place at the same time, where we're not really separating those two events, right? One way you could potentially see it kind of collapse together might be just with temperature and concentration. You may be able to see something that is really this, but it kind of blends over and it kind of looks like this. It's very, again, I fully admit, it's very difficult conceptually without an enzyme to kind of picture it, because let's say where you might see it is if I used acetic acid as my acid to do this transformation, I can say I'm using a very weak acid that must be associated with my transition state before my nucleophile even captures. Sure, that's possible now. Basically, what the closest you could ever get is some kind of an acid catalyst that isn't fully dissociated in the reaction media, right, is the closest I could say. So instead of using sulfuric acid or HCl or a very strong high dissociation acid, which will definitely be in that specific acid catalyst point, your protons are probably associated with your solvent. That's why they're all the same. It's just a bucket of protons. If you have something like a weak carboxylic acid as your acid catalyst, the proton will probably spend more of its time associated with the carboxylic acid, in which case maybe this is possible, right? Instead of saying it's transferred from like an acetic acid to the solvent, and then the solvent then transfers it to your system, right? But again, because it has this structure, you usually see it in organocatalytic systems where you've got some kind of a catalyst that has a geometric structure with a carboxylic acid, which is in a position to do a certain activation of a certain functional group. Yeah?
Would you ever see like a clean peak, or would there be a shoulder kind of?
Usually there's a shoulder, and that's where what you'll get is something that looks like almost, it's a concerted, and this is back to the point. The specific acid catalyst system is a well and true two-part stepwise. When you start moving here, it's kind of activation nucleophilic trap, so it's some continuum of those very closely associated events. Yeah?
Would you be able to even determine if there was a shoulder among the noise in your data? Because it seems like it's very easily blend together just with experimental noise.
and again, this isn't even experimental noise. The only way we get these curves is computation, right? We would have to compute the surface energy, right? The free energy surface of some transformation, and we're looking for, is there an intermediate there or not? And depending on the complete thermal energy, what solvent you have, yes, computation of what that free energy surface is may blend it out. Where you could discriminate between the two really comes down to, and I'll give you guys this as a working problem. We'll talk a little bit more later. The main difference between these two comes down to that, if you look here, the rate determining step for my general acid catalyst will be my pKa, my negative, the concentration of the Bronsted acid base, and my substrate. So it has order dependence in both the acid concentration, that negative, the Bronsted base of whatever your acid is, compared to this guy. It doesn't, the A minus component never shows up in the rate equation at all. So one other way to say this is I could run 2 experiments where I dose in, let's say, sodium sulfate into a system at some pKa, and it's not going to care about the sulfate at all. Doesn't make any difference. But if I used acetate, acetic acid, dosing in sodium acetate will increase or change the concentration of my A minus, which will then impact the actual system. So there is a kinetic order dependence on A minus for the general acid system. It's, again, experimentally they get really, really hard, and there's always a reason why, oh, you did it wrong, so it's not a great one to lean on, but that's what comes out of the rate equations that you built out. So the main point of this was just to introduce this concept that the same mechanism can have 2 very, very different flavors where we're playing around really with the size of, let's say, one of these barriers. So just bringing it back, when we show this, and we're going through these kinds of systems, as we change the catalyst, as we change the substrate, we're really playing around. When we talk about rate, which is fast and slow, reminder is we're playing around with the delta G double dagger. The stability of the system, we're playing around with the relative energy of our intermediates. And I just want to remind you guys, when we're talking through fast and slow, when you're drawing these mechanisms, you should get kind of comfortable with where you might place them on your diagram to kind of start to populate your mental image of, am I becoming more unstable as we make an intermediate? Am I making something stable as we go to our product? These are just other examples of, again, this is your chymotrypsin. This is the catalytic triad for hydrolysis of amide bonds, where your amide substrate here is actually doing a nucleophilic attack with serine, or think of it as just water on your protein surface. You have a histidine as a relay where it's passing that proton over, where the real base that's in the system is actually this aspartic acid. So again, this I meant to as a review. Have you guys seen this before, right? This is part of biochem that really, if you're going to break an amide bond, we've been told in organic chemistry, right? Go to the lab and get sodium hydroxide and try to hydrolyze an amide. No, if you do that, Nobel Prize, man. Like, come on, that's a very, very hard reaction to do. Enzymes can do it because of the structured cascade, where you're both activating your substrate, activating your nucleophile. It's this handoff event, which requires a lot of entropic penalty to make a catalyst that looks like this first, right? And really what we're doing between these two is we're just playing around with this relative barrier that we have here. We're making that first reaction barrier possible because of this extra structure we're adding to it. Anyway, let's go to this point. What I'm trying to flag here, you guys should start getting comfortable that when we draw these rate diagrams like this is a single slice through what is actually a very large surface of possible energies. If anybody's done DFT calculations, you might have done some version of this where you arrange your substrates, you calculate their energies, you put them onto this point, you draw your products, you calculate their energies, and then we can start to get out a pretty good estimate, depending on your level of theory, of your delta delta G, right? Your starting material to your product state. Transition states, we talked about this a little bit before. What we do there usually is we take the geometry and orientation of the atoms in our starting material and our product, and what we do is we walk them back and forth towards each other. We have a general picture of, if I'm saying some substrates have to turn into some products, you can build a 3-dimensional model of what that transition state might look like. If you go back to SN1, SN2, we know that if you're going to do an SN2 reaction, I need 180 degrees of my nucleophile and my leaving group. I line those up, and what I'm doing along there is I am creating a state where if I move Z closer to Y, if I move Z closer to Y, I'm going back to this starting material. If I move X closer to Y, I'm going back to my product. So you can imagine the transition state is this frozen picture where it could decide in either direction. I'm going back to my starting material or going back to my product. And it's really just about which bond distances you are expanding or contracting. That's that vibrational energy that you're sort of talking about, that if I extend or I lengthen my YZ bond distance, I'm sort of moving towards my product where I'm dissociating. If I extend the XY bond distance, I'm going back towards my starting material. So both of those are possibles in terms of their trajectory or their size. Which this means is you can kind of imagine a continuum where if I was to graph the energy of those molecules as I push X closer to Y and as I stretch Y away from Z, that's why you get this elevation in energy up to the transition state. This is the point where the energy sort of spins around, where continuing to push this away gets you towards your product. And you can imagine making a movie of that process where the energy is rising as you get up to this transition state and falling down. That, though, is actually one channel on what is actually a much larger three-dimensional surface. So, quick snapshot. Has anybody ever seen this kind of a diagram for when we're talking about making and breaking bonds? Like, you guys have seen this. Really all we're doing is this is a two-dimensional representation of this three-dimensional surface. So going back to like this example, what we're talking about is I could actually take, let's say I'm doing the reaction where a nucleophile is approaching my carbonyl. The carbonyl is being activated by my acid. If I were to do this where the nucleophile has to attack that carbonyl, it's not involving the proton. So we're saying now that the nucleophile attacks the carbonyl first. That goes through a high energy event to make this anionic intermediate, where that oxygen then grabs a proton to get to my final product. So all I'm saying is here is the reactions, the specific bonds that are formed and broken, this is no different if we're talking general acid catalyst, specific acid catalyst, any nucleophilic addition to a carbonyl is just the order of operation of a nucleophile has to approach the carbonyl, we need to break a carbon-oxygen pi bond, and a proton has to transfer from whatever acid source it is to the oxygen, right? That's the kind of the bin of all things on the recipe to do this transformation. The surface I'm showing you here, though, shows in this example, the first step is my rate-limiting step. It's the biggest barrier. Why this might happen is I'm saying I'm exclusively focusing on a nucleophilic attack to make that to the carbonyl first, to make an oxyanion. The oxyanion then picks up a proton to get to my product, right? So that's that system. If you had to translate that example back to a chemical example, where might this persist? Like if I did this reaction, and I want to go by this kind of a pathway, nucleophile first, proton later, what nucleophile might fit this bucket? An amine? Okay, why? You're not wrong. I think I get where you're going, but give me a rationale. Why do you choose an amine?
Typically for reductive amination, you need to choose a specific acid.
You're talking reductive amination. But still, I get what you're saying. You know, in reductive amination, the nucleophile needs to attack first, right? So part of it is look at the relative stability. If your nucleophile, in this case, is like you're going to this higher energy intermediate, the good nucleophile is what we'd stick to. This might be something like a T-butoxide, right? An hydroxide, something that's a strong nucleophilic species that still has to, be not so basic that it just grabs a proton off your HA. That's kind of one of the other acid-base pieces here. If you did this with like a Grignard, maybe, like a nucleophilic Grignard attacking a carbonyl might precede the proton transfer in that case. So some of what you're seeing here is you have to match it to the right kinds of reagents, one part. It generally follows what we sort of describe here, that usually a good nucleophile to make a relatively stabilized intermediate and then fast protonation after might happen. But if you look at this transition, what we're trying to emphasize here is this two-dimensional presentation. If you go out to look down on top, so imagine if you were looking down here, you can represent this transformation on a 2D surface where if I'm viewing this, this energy surface, from above, I can break that down into a nucleophilic attack first to make a tetrahedral intermediate, and then after I make that tetrahedral intermediate, I then do a protonation. So those are two discrete steps, 1 and then 2, right? You could do the other too, where maybe if this was acid catalyzed, maybe we protonate first and then we nucleophile attack. So this representation, when you start looking at in this two-dimensional surface, you're taking every operation of bond forming and breaking that you've been doing, and now you can say I can remix them in any order for different substrates and different catalysts. Maybe I'm going to see nucleophilic attack precedes protonation. For different catalysts, maybe protonation precedes nucleophilic attack. And then you can have in between where they happen identically at the same time. Protonation and nucleophilic attack happen simultaneously. So you have three possible mechanisms now where the first attack happens, or attack and then protonation and then attack, or the full general acid catalyst where everything happens simultaneously. When you're looking at this surface, this is where what we have to do, depending on the species you have, you can go through and calculate which of those paths is most likely, because now you're looking at a topology of a full-on energy surface. Depending on what the structures are, you can get a case like here. This would be that perfectly diagonal attack. If I have a surface, and this is what the three-dimensional energy surface would look like, I'm starting over here as my reactants, I'm ending up here as my products. In this case, this might be a diagram representing what could be just a substitution reaction. But you can get the version of like, I will get nucleophilic attack and elimination all simultaneous with each other. And what we're really saying in that case is I get starting material to product through a single transition state. This is your saddle point on your surface, which means I am actually following an SN2. That's what this diagram is really showing is for some particular set of substrates, it's possible that that concerted attack gives you this diagonal sort of intermediate. Versus one of the two other stepwise ones, SN1 might be what you show here in dotted. I might get breaking one bond to make a carbocation or carbanion, and then forming the next bond. So this 1,2, it's the same composite reactions, but your surface would actually look different. In that case, the low energy, this saddle point, would exist probably over here in this corner. It's in the shoulder where what you're saying is it just happens for that system that making the carbocation is favorable compared to that sort of bimolecular attack. The part I'm trying to emphasize with this is when you have this option where the same bonds can happen in different order, this is the kind of thing that you should pop up in your mind, that it is kind of like the principle of microscopic reversibility. Every possible bond break and bond form may happen. Which one persists for certain mechanisms comes down to which order of operations gives you the low pass in the diagram. Really what we're showing you here is think about these flat energy surfaces here instead of like this. It's a mountain surface. Yeah, please.
I was just wondering, how do you know how many saddles or peaks you have in the top-down view?
When you're looking here, sorry,
In the bottom left corner. You have-
in this one here.
Yeah.
You don't implicitly. Like the point is, what you would normally do, how you would get this, I would take my starting materials, I would take my products, and I would basically, if I was doing this for an SN1 reaction or SN2 reaction, I would take every position, I would create a case where I have, here, think of it this way. Sorry. I take, let's say, my middle, which is my Y, and what I'm doing is I'm saying I have some starting material where I have my YZ bond, and I have a distance associated with that, right? And then I've got my next one, my X, and I've got that bond distance. So we're going to call this bond distance A, and this bond distance B. Okay? So I've got my system set up, and what I'm trying to ask is, does X approach Y and Z break? Does it happen concerted? In which case, as A shortens, for every time I lose 1 angstrom here, I gain 1 angstrom here. Right? So you can imagine what you're doing is I'm taking my top-down view where I have the, let's say, YZ bond distance along this axis, and I have the XZ bond distance along this axis, right? And for start, I'm starting in this top corner where the YZ bond distance is some value, and the XZ bond distance is, does that make sense? Sorry, yeah. X, Y. I want to start out, it's not bond distance. It's not bond distance, call it degree of bonding or something. If we wanted to do it with distance, it'll look slightly different. What I mean is, up here, we can agree that the YZ bond distance is some value, let's call it 10, right? If this was the XY bond distance and there's no bond between the two of them, let's say it's very large, 100, right? So let's say I'm starting off and I'm trying to define the starting material state. At the starting material, in the starting material, Y and Z, they're bound to each other. That distance is small, right? X and Z, the distance is very large. If I was doing this by distance, so forget this guy for a second. This is reaction coordinate, but let's imagine it in terms of actual distances. So if I'm going to start this where Y and Z are bonded to each other, they're very small, that should be here, right? On this axis, it's going to be a small value. And if I'm breaking the YZ bond, it will increase as the reaction progresses. So I'm going to define this where my starting material, YZ is some small number, I'm going to call it 1, and I'm going to increase it as the reaction progresses. Likewise, at the starting material, the XY bond distance, it initially starts very large because they're not bonded to each other. So that would be over here in that case. So that in that diagram, let's say this is 10 angstroms and it's going down to 1 angstrom. This bottom corner defines the geometric presentation of the two different bonds I'm trying to describe. It's small along the YZ axis because they're bonded to each other, and it's large across the XZ axis. They're not bonded to each other. Make sense? So this corner here would represent by distance my starting material, right? Now, I have a choice. If I'm going to move X closer to Y, and at the same time I need to break Y to Z, I could do this in one of three options. X runs into Y, and I never change my YZ bonding axis. So that's like taking my nucleophile, I run it into my center, and I don't break the other bond. Okay, everybody on board with that? What do you think happens energetically if I did that? So let's put this into specifics. If I had hydroxide's my nucleophile. We're going to call hydroxide, that's my X. Chloride, isopropyl chloride, where this is my Y. That's my carbon species. The thing that I'm leaving or breaking, chloride is my Z. Okay? We just said we started out where the YZ bond distance is small. We're bond. YZ bond distance is small. The XZ bond distance is very large. They haven't approached each other yet. That defines that bottom corner. Now I'm going to try and move only along this axis. I'm going to contract the YZ bond, and I'm not going to touch the, I'm contracting the XZ bond. I'm not changing the YZ bond. If you look back to this, what happens here? Yeah, we're smashing hydroxide into the center, and we're not losing anything else. Texas carbon, right? We're over-hybridizing that center. So on the energy surface, starting from this bottom corner, where the nucleophile is distant, but the bond is happening, and I just move only along the x-axis, we know this is crazy, right? That's going to be and we're basically doing fusion there. So no, this is not a corner energetically. The third axis I would be looking at in that case would not exist, right? Too high energy. Okay, let's do the opposite. if I was, for the same system we have here, so hydroxide, isopropyl chloride, let's only move along the y-axis. I will start here, and I'm just going to, without changing the xy bond distance, I'm going to stretch the yz bond distance. I'm going to do this. So what am I doing in my diagram over here? If I do not bring in my nucleophile, not contracting it in, but I'm only stretching yz, what happens here? This is SN1, right? I am taking this bond, I'm stretching it out, I'm making a carbocation, and I'm making now, if you look at the system, I have a hydroxide carbocation chloride system. Happy or unhappy? It's not as bad as thermal fusion, right? But it's probably pretty high energy up here. You're making a carbocation, especially you're making an ion-separated carbocation when you have a pretty good anion somewhere nearby. Okay, so the third option is we do both at the same time. I go diagonally. In that case, every time I walk the hydroxide closer to my carbon center, every time I compress my XY bond distance, I also lengthen my YZ bond distance, right? So if you did that, you'll find some point halfway in here that if I was to imagine this from the top, I can imagine that over here, this is crazy town. This is the high energy surface over here I'm never going to get near. Over here, I'm expecting this to be pretty high energy as well. But down the middle, that should be lower energy, I believe. And again, this is just my expectation. How you would build this is, I would take every one of those different positions, I would build it and say to a DFT program, you're not allowed to move my atoms. Tell me what the energy of this presentation is, where I've put my atoms and how far they are. So you would literally build this, run the calculation. Move it a little bit, build it, run the calculation. You could actually do every version of this X, Y, and YZ bond, and what you're getting, that third axis, is the DFT calculation that tells you what the energy is. After you've done that, that's what you build in the bottom left corner. You get a surface that represents each of those nodes of every single geometry that could have happened across every single atom presentation. And then once you see that, you're like, that's clearly diagonal down the side. That must be a concerted pathway. This is SN2, right? So it's not a priori, unless you know a lot about the mechanism, you couldn't draw it. You would create it this way where you try each presentation and then we come out and say, this is a concerted process because that diagonal allows me to make that conclusion, right? If we change the system and I did this, hydroxide, and if we did, let's see the identity reaction. I'm going to take, let's say, labeled water attacking isopropanol under acidic conditions. That's a classic SN1, right? That's a case where the nucleophilic attack of this water onto this center and kicking this one back out, that diagonal, probably not awesome. Better is probably protonate this, make the carbocation, and then this one comes in. At very least, this corner here, those kind of two separate reactions, at least is no better, no worse than this diagonal, right? So that's how you would build it. But the point I'm trying to emphasize here is every time you've seen a mechanism where the same kind of bonds are forming and breaking, and you ask, well, why did that order happen? It's because of some calculation or a mechanism that was done like this that says that particular order of operations presents a lower energy pathway on this 3D surface. You're not wrong to saying that it could go in a different order of addition. It's just that you can kind of work out this process of elimination. This is one of those cases where, like here, overhybridization, that's nuclear fusion, definitely out of point. But in these other cases, it depends on which acid you have, what system, what stabilizes. And you want to kind of expand, and we'll be talking a bit more about this in the next couple classes. This is kind of the visualization I want you guys to have in your head, because this is really what's going on in catalysis, is you don't have the 2D representation, you have this 3D surface. And as we go through and change substrate and catalyst, what you're doing is you're adding valleys to this 3D surface, which allows these other pathways. So it's nonlinear in the end. Cool. All right, see you guys on Friday.
So hey guys, I just wanted to go through and kind of write out what we sketched on the board because I think it's relevant. What I was trying to do in class, what we were sort of discussing, and I apologize that we didn't have the iPad working today, is kind of just work out the kind of ideas or the understanding that you were kind of showing in this kind of topology type graph. So what this representation is showing down here is saying that if you had a reaction where we are forming a bond between this X and Y while we're breaking a bond between Y and Z, we pass through a transition state where a new bond is forming while a new bond is breaking, and then we end up with our products where there's been this exchange. We now have a tight bond between X and Y. We've completely departed this bond between Y and Z. So in this formation here, just for convention, we're starting in this top left-hand corner. That's our reactants. We're saying that the bond order, or at least the composition, we have a tight bond between this YZ and the nucleophile X is not present. This is also, you probably recognize as a reaction coordinate for something like an SN2 reaction. Now, what I was describing in class, what's shown here is sort of the, I'll call it the reaction coordinate, but I was trying to ground it a little bit more into something tangible, because it's, in my head, it may be a little bit easier if we look at in terms of bonding distance. So I'm going to show this with result to a specific system. So let's say I've got a carbon, it's going to be tetrahedral, so just hydrogens. Let's actually be fully, I'm going to be explicit here, and I'm going to draw this as a bromine as my leaving group. I've got methane, so it's a methyl bromide, and I've got a tetrahedral carbon here. Okay, and I'm going to take another nucleophile. We're going to do what's called an identity reaction. So I'm using bromide as a nucleophile with another bromine as a leaving group. The reason I'm doing this is because the starting material and the product in this case have absolutely identical energy. It's perfectly symmetric. It's something that you can document really easily, and you know that the energies, what the energies have to be. So what I'm documenting here is, let's say, the bonding distance between this bromine and that centered carbon, and I'm going to call that the carbon-bromine bonding distance, where it's this red bromine here, and over here I'm going to call this my carbon to bromine, where that's my blue bromine over here, distance. So along this axis here, up and down, I'm going to plot my blue carbon to bromine, my blue bond distance. And at the very beginning of this, where I'm starting, where I have my nucleophile is separate, I'm going to say this distance here is very, very large, and the carbon-bromine bonding, let's say the distance is very small. So on the specifically referring to that bond, I've got, let's say, a 1 angstrom carbon-bromine bond. At the same time, at this starting state, I've got my bonding axis. Here, let me just move this up a bit. Over here. In the starting state, my carbon to the red bromine, this distance right here is very large. So I'm going to be out there. Let's say it's 10. It's 10 angstroms away. I'm starting somewhere very far away. And I'm just saying that's positionally where I'm starting. So it's at this relatively short carbon to blue bromine and a very long carbon to red bromine bonding distance. Okay, now we're going to start putting in motion. And we have 3 different trajectories you could imagine. So we're going to call trajectory number 1. Trajectory number 1, we're going to start at this position, and I'm going to only compress this carbon to red bromine bond distance, while I'm not going to touch the carbon to the blue bromine bond. Effectively, what I'm doing there is I'm taking this bromine, I'm bringing it into the center, I'm shortening this carbon to bromine red bonding distance, but I'm not elongating this one at all. I'm keeping it constant. That's why I'm moving along this axis in this kind of linear pattern, right? Now, if we did that, we're going to hit a point where the carbon and red bromine bonding distance is very, very close, It's already at an octet. This center here is completely unreasonable, right? This would be equivalent to drawing something like my carbon bromine is fully bonded, short bond. I'm going to have my hydrogens sticking out like this, and the red bromine is effectively stuffed in there like that. So this would be like a pentavalent carbon, where I've actually got a full bonding order here and a bonding order there. Not possible. Way too high in energy. So we're going to stop there. That trajectory doesn't make sense. We're not going to do this one at all. Okay, trajectory number 2. So in this one, now what we're going to do is something that's symmetric. Let's do the opposite geometry first. I'm going to take this carbon-bromine bond here, the carbon to blue bromine bond, which is represented on this axis. Even though I'm starting short, I'm going to elongate that bond first. So what I'm doing is I'm stretching this carbon to bromine bond. I'm making it much, much longer while I'm not bringing this red bromine closer. That's why I'm going vertically up this way. I'm not changing along this direction yet. So I'm not actually shrinking the carbon to the red one. So that would get me to something that would look like a carbocation, right? In that top corner, I would have something that would be my planar, fully dissociated carbocation, where I've got a bromine minus, and the bromine plus hasn't come closer to the center yet. So this is the fully ionized protonated center. Again, this is pretty high in energy, but it's least possible, right? We're not breaking bonding orders here. We can talk about the relative stability of this one. You know, it's a primary carbocation, so it's relatively high in energy. Some debate of, is this worse than this? But we can tell that basically these two corners are both very high energy points. Now, at least it's feasible. We could then collapse this center in. So what we're saying there is then we bring in this bromine into it. And what you should notice is this pathway moving first up. So this kind of dissociation followed by association, that would be the classic SN1 pathway, right? We're forming a carbocation intermediate, and then we get nucleophilic capture. The last option would be to go, let's say, along the diagonal, a concerted pathway between the two. So in that case, we're both moving closer in the carbon to the red bromine as we're elongating the carbon to blue bromine. So what we're doing is simultaneously increasing this bonding length here as we are decreasing the other bonding length. And we follow this diagonal path as we go through it. That's going to pass through a point somewhere halfway that's going to look like our classical transition state for an SN2 reaction, where you have this kind of partial bonding order to both cases. Blue bromine is on the way out, the red bromine is on the way in. This is sort of moving closer while that we're moving away, and we have this kind of half-half, or like a partial bonding order between both. So it's still higher in energy, but we're along this kind of diagonal point. So those are kind of represent the three possible extremes, right? We collapse the carbon to red first, or we stretch the carbon to blue first, compared to the concerted one there. And this is just sort of the three different continuums that are kind of possible. So really what we're representing is that any two-dimensional representation you see like this really is talking about a convolution on some kind of a three-dimensional energy surface, where the relative bond breaking or bond forming events could happen in any of the possible orders. Like we could break the YZ bond first and then form the nucleophilic XZ bond, or vice versa. And it's through that sort of order of operation that we get these different permutations to different reactions. In the next class, we're going to talk a little bit more about that in reference to the acid catalyzed system.